This is joint work with some of my fellow students at KIT and my advisor, Frank Bellosa. And as already mentioned, I will telling you today how to save memory in virtualized environments by getting more effective deduplication scanners through cross-layer hints. So the problem is that when consolidating many virtual machines onto fewer hosts in the multi-core and many-core era, the primary bottleneck that you hit is actually the main memory size. And fortunately, in those scenarios, there's often a considerable amount of memory pages that are actually the same, they contain the same content. And different research group has shown this in varying degrees, as you can see in this table. And this gives us a great potential to free memory via copy on write sharing. And of course, if you have matching operating systems, matching applications, libraries, and data, this potential is even greater. But fortunately, cloud providers can even choose where to consolidate their machines. So they can even choose to migrate their machines to a host that can maximize the sharing potential. So our goal is to merge pages to free memory for additional VMs. Unfortunately, this cannot be done with traditional sharing mechanisms, as these mechanisms are generally based on a source object instead of content. For instance, fork can share address spaces between parents and children. But even if you, for instance, start two programs in two different shells, and then the two resulting processes could not share any memory except of their shared libraries. And those shared libraries, in turn, would be shared through the AMAC mechanism. And it is enough to copy those shared libraries to stop the traditional sharing mechanisms to work, as those are based on the inode, the source inode, and not on the source content. And virtualization actually introduces this very semantic gap, as VMs generally ship with their own virtual disk image, and this disk image contains its own file system with the own binaries, libraries, and data, and this copy semantic is not known to the host, so the traditional mechanisms don't work here. So OS developers or the OS community in general has asked themselves how to identify pages with equal content in order to share them in the past, and they've come up with two different solutions. First of all, the solutions that I'll call the para-virtualization or introspection-based solutions that are aiming to close the semantic gap by creating an appropriate interface or by doing introspection into a well-known VM that they're running. And the observation here is that often memory duplicates are created either directly in memory by copying with calls such as memcopy, or they actually stem from the disk, and those would be files, or, for instance, programs or libraries, or even data that is processed. And the assumption in these types of systems is that you can actually observe duplicates from being created. And the previously developed systems, the previous developed implementations are based on the assumption that you have some form of content-aware sharing in the block device, and then you either watch which addresses are accessed on this shared block device, or you actually implement this block device in the guest, and then have some sort of transportation mechanism to share the semantic. The other thing that these systems have in common is that they actually deduplicate synchronous to the I/O, meaning they actually stop duplicates from being created in the first place, which might and actually does give you some form of overhead when you run I/O-intensive applications. The other downside that these systems have is that you actually need to be able to change the guest OS, which might not always be possible. So if you want to share memory in non-para-virtualized systems, so if you're not able to change the guest, or if you're running a non-para-virtualized system, then you can do this with a memory scanner, and VMware has first developed this in 2002, and This system was later also adopted by Linux under the name kernel same page merging, or KSM. And what main memory scanners do is that they continuously catalog page contents regardless of their source. And they do this simply by scanning, like waking up and scanning a couple of pages and building an index of infrequently modified pages. So they first filter out frequently modified pages and then build an index of the other pages. And while inserting pages into this index, you find duplicates and merge them. However, there's a trade-off here. As you can see, you actually pay for your memory density, you pay for the saved memory with CPU cycles, and of course, that's the more important part, with memory bandwidth overhead. And please keep in mind that even if you run this at a very aggressive scan rate, you still cannot reach instantaneous deduplication as you would in the para-visualized solutions. And to give you an idea of the overhead, I'll show you two settings that we used in our benchmarks. We actually have used 3, but those are the 2 upper and lower ones. And as you can see, in an aggressive scan rate that scans about 5,000 pages in a second, you still need about 1 minute to scan a gigabyte of memory, although you need 70% of a single i7 core to scan. And we've actually seen that this is a problem by running some initial benchmarks. In this case, it was a kernel build with 2 1 gig VMs. And we've seen that we've actually run this in a memory tracer in a full system simulator in SIMIX. And we've seen that more than 70% of the pages that could have been merged were actually not indexed by the scanner before they were changed. So they were never shared. However, those pages were actually shared, they were actually modified late enough so they would have been a good sharing candidate. Sometimes those pages would have been not modified for minutes. So the state of the art when we started this project was that on the one side there were the para-virtualized approaches that did a very good job in deduplicating specifically considered sharing opportunities if there was no I/O pressure. And if you were possible, and if it is possible to change the guest OS, and there were memory scanners that treat all memory equally regardless of semantic, and there is no need to modify the guest OS, but you can only share pages that live long enough. So we asked ourselves if we can combine the two, if it is possible to get some more semantic into the memory scanner. And it turns out that the answer is yes, otherwise I wouldn't be standing here. And what you can do is you can actually intercept I/O purely in the host, record the target memory areas that this I/O interacts with, and then prioritize the recorded memory areas in the memory scanner to achieve a better deduplication ratio. So as you can see in this example, intercepting I/O in the host is actually trivial, as the host or a hypervisor generally already performs the I/O on behalf of the guest in the first place. So if, for example, GCC would read a file in a guest OS, then this read would go through the virtual file system in the guest and would be in the actual file system be translated into a virtual block read to the virtual disk image. And this virtual disk image would then be, as the virtual disk is just represented as a file in the hypervisor, would again be translated into another virtual file system call in the hypervisor, and then to this VDI file, to this virtual disk image file. And this is our insertion point. This is where we record our hint. And then we would follow along with a regular I/O path to go to disk to read the file from the actual disk. So please, in this scheme, please take keep a couple of things in mind. First of all, of course, we do not need to modify the guest, but also we're very, very, very generic. We don't even need to run virtualization to get I/O hints here. So if we ever decided to run deduplication in native applications, and actually this is becoming more and more reasonable as we run more and more appliances and zero install applications and so on. We could still use a system like this. And the other thing I would like you to notice is that in my example, we actually had a physical disk and a virtual disk image that comes from there. Usually this is not the case. Usually you have some sort of network-mounted file system where the images reside in. But this is no problem for the system either, as actually you can generate hints from anything that mounts. So a network file system, for instance, that is mounted through in the hypervisor could also be used as a source for hints. The second building block in this system is the storage part. And as I've told you, you don't actually want to process all I/O synchronously and dedupe on the fly. And Satori research has actually shown up to 35% slowdowns in file system benchmarks, such as Bunny++. And fortunately, memory scanners already have that property that they don't do that. They actually defer processing of hints or of the regular scan to smoothen out the I/O workload. And it's very easy in memory scanners to actually limit the resource consumption. The problem with that is that you might not be able to process all hints that you generate. So there's a trade-off there too. And at first we tried to keep all our hints in an unbounded queue, which turned out to be not such a good idea, as when you don't bound your number of hints and your IOPS are actually always larger than your scan rate, your queue would grow and grow and the hints would go older and older, and after some point those hints would actually be processed after the linear scanner would pass those pages. So this can clearly break. And even if it doesn't come this far, old hints make finding short-lived sharing opportunities, which is our goal, less likely. And also when you process old hints, you actually shorten the time that a page may remain shared. So this calls for some sort of pruning or aging mechanism in the hint storage data structure. So we actually implemented something very different. We implemented our hint storage in a bounded circular stack, which actually gives us all of those properties that we want. It keeps semantically, it keeps the last unprocessed stack size disk accesses, and the stack part of bounded circular stack returns the newest hints first, which maximizes the sharing time. And the bounded part actually gives us an implicit sharing and aging mechanism, as the old hints are overwritten when new hints are pushed. The third building block of this system is the processing part, and KSM already provides us with all of the mechanisms that we need to implement this. KSM already wakes up at certain intervals and processes a certain fixed number of pages, indexes them and merges and so on. And we've decided to interleave the hint processing with the regular linear scan process. And this gives us some nice properties. For instance, we will never starve the I/O process. So even if there's a constant flow of I/O requests, which is faster than our scanner, we will still be able to catch duplicates from both kinds of memory, from file-based memory and from anonymous memory. In our implementation, if the hint buffer turns empty, then we actually switch over to the regular linear process, and this gives us a property that we always keep our scan rate constant, and that makes it very, very easy to compare the two systems at equal work settings, like at equal workloads. We've actually run many different benchmarks, and they're all in the paper. I'll only present two here, so please refer to the paper for the other benchmarks. In this benchmark, we just ran two virtual machines with 512 megs of RAM and Linux, Ubuntu Linux, and they were both building the same version of Linux and the same Ubuntu virtual machine and so on at the same time. And first of all, just from the run times, we were not able to distinguish our system XLH, which by the way stands for cross-layer hints for those who ask themselves, and KSM, the vanilla implementation in Linux. And in this graph, a higher line means that more pages are shared and that more memory pages are saved. And before we actually ran the two systems, XLH and KSM, we first determined the possible amount of sharing. And we've done this by doing 1 second snapshots and then doing an offline analysis of those snapshots. So we just counted how many pages were the same in those snapshots. And this is the black line on top here. And that line peaks at about 37% in this workload. And as you can see, our improved version, our improved memory scanner actually almost traces this line, while the vanilla implementation at the same scan rate, so when you put the same work into deduplicating with the vanilla implementation, you actually can only barely keep the amount of memory that you could share at the beginning of the workload. The other thing you can see here is that even if you turn the scan rate down by a factor of 10, we can still compete with the vanilla implementation that puts 10 times more effort into scanning. And as I mentioned earlier, the idea is that we want to find short-lived sharing opportunities in addition to the long-lived sharing opportunities that were found by KSM already. And when you look at the sharing times that that the distribution of sharing times in the two systems, you can see that this is actually the case in our system. You can see the red graph, the red bars are much higher in the short-lived area than in the end. And to share that much more memory when only gaining from short-lived sharing opportunities, we actually have to find way more different sharing opportunities than KSM, and we've also confirmed this in our results. You can see here that in this benchmark we almost find 10 times as many sharing opportunities than KSM does, and we actually are able to merge pages that both systems merge 4 minutes earlier in the median. When you look at a different, more interactive benchmark, such as this one, where we run 2 different Apache web servers against a HTTP client on a different host, where we actually generated files that would not fit the main memory of the virtual machines to be served and shuffled those files to be served at different times in a different order in both. So the same files would be served at a different time in the process in both VMs. And then again, first of all, we can see that we have measured that the throughput and the latency of HTTP does not show us a difference, but we still vastly outperform KSM in this benchmark. We again almost trace the amount of sharing opportunities in this benchmark, while even our version that scans 10 times, that puts 10 times less effort into the scan, outperforms KSM in this benchmark. Of course, you now will ask, well, those two benchmarks are clearly in favor of your system. What happens if you run something that doesn't have the property that all or most of the sharing opportunities come from files and so on? And first of all, you have to think about what a bad worst case for us would be. And if there's nothing to share, then there's really no difference, as we actually, both XLH and KSM, put the same effort into the scanning process, and there's nothing to share, so nobody shares anything with the same effort. If there's no I/O, then we don't generate any hints, and the entire quantum for following hints goes to the linear scan, so there's no change here either. So the real worst case for our system is that there are a lot of sharing opportunities, but most of those sharing opportunities actually do not come from files, which is, as you can imagine, already a rare case. But and actually in practice, we've looked looked into it, and we've run benchmarks with different Linux versions and different workloads at the same time, and measured this, and measured how many how many duplicates we can share, and actually we came out on par and did not any worse than KSM in those benchmarks. But theoretically, you can write a synthetic benchmark that would do I/O on a single page that cannot be shared at all times. So the scan progress would be halved in this scenario. So theoretically, theoretically it could be possible to find a workload that would make the scanner scan at half the speed. But if that ever was the case, that wouldn't be a biggie, as we actually can easily track which merges come from our hinting mechanisms and which merges come from the linear scan. So if we see a large mismatch between those two numbers, we could easily just tune the interleaving ratio down or shut down our system altogether. And this can easily be done at runtime, so it's no problem. Last thing I want to talk about is the overhead. And I've already said that latency-wise and runtime-wise, there's really no difference to the vanilla scanner. But even if we measure the CPU consumption of the scanner thread, we have only seen a variation of about 6%. So we actually don't do that much more work than KSM does. And when we look at disk throughput, and this is the benchmark where Satori actually showed slowdowns up to 35%, of course, this is a very unfair comparison to Satori, as we can tune our scan rate to a setting where we don't see any slowdowns for us. But when you compare KSM and XLH, we also only see an increase of about or of less than 4% when running file system benchmark in our aggressive scan rate with such as like Bunny++. And this shows that our hinting mechanism is actually very, very scalable, very, very fast. Like we don't lose a lot by intercepting the I/O and storing all I/O in our buffer. The other thing you might ask would be, well, you need more memory, you need a buffer and so on, so don't you actually lose in that regard? And to this I can say that the largest hint buffer in our benchmarks that we've used was actually only about 2 megabytes in size, so we don't have to put that much memory into the process to gain in favorable workloads. To conclude the talk, as we all know, main memory is a scarce resource in virtualized environments, and deduplication helps mitigating this effect. Memory scanners can find long-lived sharing opportunities, while para-virtualized systems can find short-lived opportunities at different costs. XLH is the combination of the two. It can deduplicate pages from all sources while giving an emphasis on virtual disk-based sharing opportunities, and it is possible with XLH to deduplicate those pages much, much more quickly than in regular scanners. A lossy buffer copes with bursty I/O and with I/O overload without much overhead. We still have the properties from main memory scanners that we have a configurable, limited overhead and no need to modify the guest OS. On a favorable workload, XLH can actually detect about 10 times as many sharing opportunities as a regular memory scanner could, and it can share those sharing opportunities earlier by minutes, while XLH can actually easily detect a non-favorable workload and then disable itself or tune the system down. Thank you for your attention. Any questions? Anybody awake?
From VMware, I think you pretty much point out the weakness of your assumption. You're assuming I/O blocks are more shareable than random blocks, and this is a kind of tricky assumption. I can see if I run two kernel compilers and on the same Linux version, yes, that's true. But I can also imagine that two people watching the same movie, and in that case, it's not true. But I think you should spend more on your basic assumption.
The point here is actually that in large computing centers, such as Amazon, like Amazon EC2, has so many workloads that they can actually choose where to put their data. And actually there has been work on that previously, like memory buddies, for instance. I think the author sits in the audience somewhere. So it is actually possible to find workloads that are close enough to make it worth putting them on the same host to deduplicate.
Yeah, it would be nice to see some statistics to back up your claim, especially if you mentioned Amazon. If you have some Amazon chase that show, okay, I do have such a lot of opportunities, that would be great.
Yes, I agree. Thanks for the question.
Matthias Payer, UC Berkeley. I actually have a wider, more open question. Think about using your approach in a cloud environment and you're running multiple virtual machines. Could you use your approach, or if an attacker knows that your approach is used, could the information be used as like some side channel attack that you know that what kind of code pages the other machine already maps, and you can use that to extract data?
Yes, there's a paper on this at EuroSec 2012.
Nice. So I should read that.
Yeah.
Thanks.
But that's like, we're not different than the like regular vanilla there, but the vanilla KSM there, but yeah, that is actually possible.
Wei Xu from VMware. I just have a question regarding the short-lived sharing opportunities. So I think one problem with page sharing is that if you need to break sharing, then you can incur the overhead. If you share a lot of short-lived pages, so will this have a big performance impact to the workload? So what's your experience with that?
Yes, if you degrade to a system where you share everything, but you write those pages right away, like you deduplicate very quickly and then write them right away, that could actually degrade performance. We haven't seen this in our case. And as you can see in the benchmarks, we have only shared, we go to a level where we share pages that live for at least a second. And this is actually still not too quickly. Like if you go down to sharing opportunities that only live for a couple of milliseconds, then you would probably see a difference, yes. You could, if you ever went into, if you reach such a situation where you say, oh my God, I'm merging too fast, you can always wait until you reach a certain time in your buffer, right? So it's actually, you can actually really easily hack this to share pages that live at least a certain amount of time, like to cut out all the very short-living opportunities. Does it make sense? Actually, there's much more sharing opportunities if you go to very, very, very short snapshots. Like we've run this in USENIX, and we can see that you can actually find a multiple of this in sharing opportunities if you go down to like cycle granularity.
I guess basically, I think the takeaway is that with the kind of length, you choose whatever second or whatever. So the performance still pretty good, and there's still a lot of sharing opportunity. Is that right?
In our benchmarks, we've not seen the performance degradation, but I can't tell you what the magic number of, what the magic seconds is that it can be shared or not. The problem is you can't really define the break-even time, right? Usually you would go ahead and say, okay, we'll define a break-even time that is the work we have to put into it, and this is what we have to get out, right? But there's no such thing, because what would the break-even point be? Energy? Maybe? I don't know. It's hard.
Thank you.